Alright, today we are going to be talking about sound and how it travels through materials. We're going to talk about ultrasound, infrasound. We're going to talk about the nature of sound itself, the speed of sound, and how it changes in amplitude, wavelengths, and frequencies of sound. So, what is sound? Well, sound is a longitudinal wave. Remember, that's where it compresses and rarefacts or spreads out through air, or liquid, or earth. That's kind of an important thing. That sound doesn't just travel through air, it travels through water as well. You can actually hear this when you go under a pool. If you dive under a pool, listen, you can actually still hear. It's muddled, but you can still hear. And in solid earth, you can actually hear that as well. If you put your head on a desk or a table and tap it, you can still hear the sound through the table. So it's that longitudinal wave. But one thing that sound cannot do, and that's because it's a mechanical wave, it cannot travel through a vacuum. It is that vacuum is perfect. If it's a perfect vacuum, like space, you can't have it. So when the Death Star blows up, no sound. Now, when objects vibrate, they move back and forth in air and produces sound. The sound carries the energy. Remember, waves carry energy, not the material, to our eardrums or to a microphone, and that's how we are able to hear. So in this, we're going to watch a vacuum demo. Now, the speed of sound wave depends on the density of the medium. We kind of talked about this earlier. Traditionally, the more dense the material is, the faster the sound will travel. And it travels faster through earth than water, faster than water than compared to air. The speed of sound in air is about 330. It's actually 347 at room temperature, but 330 is a good number. That's a good average. But in comparison to light, light is so much faster. The speed of light is 300 million meters per second, compared to the 330 meters per second. So the speed of light is thousands of times faster, or millions, not thousands, millions of times faster than thunder, or so through through air. Now, speaking of thunder and lightning, is what I was thinking of, is the idea of when you see a flash, you hear that 3 seconds later, the sound of the thunder comes. That is very true. That is actually what you are seeing versus what you're hearing. So, here are some various speeds of sounds through other materials. We have hydrogen at 1286, helium at 900, air at 343, air at 0 degrees 331, and then through some liquids, you can see that water is at 1493, solid materials even faster. Diamond is at a ridiculous 12,000. And this is just due to the fact that the atoms are closer together, so they're able to transmit that energy faster and easier. Now, density does play kind of sort of a part of it, but so does what the atom arrangements are, so the chemistry of it. So diamond is not as dense as iron, but diamonds, because of its arrangement, allows it to be faster. Now, sound loudness is dependent upon its amplitude. So the bigger the amplitude, the louder it is. This is how, so if we get it, that's how you typically hear it getting louder, is because you're increasing the overall amplitude. And we measure that with the decibel scale. So you probably have heard this. The decibel scale is a unit describing that pressure level of that wave. So that sound wave that produces that pressure, and then the opposite, that rarefaction or spreading out, that low pressure, and pressure again, low pressure, and that back and forth, those are where you have that hearing, that loudness. Now, 0 decibels is basically the threshold of hearing. You can't hear anything less than 0 decibels. Rustling of leaves is 10 decibels. Country residence, 30. Average office. An orderly conversation 3 feet away is about 60 decibels. So you're probably listening to this at about 50 to 60 decibels. Not too loud, not too, it's not soft by any means, but it's definitely somewhere in there. Boeing 737 departing off a runway, measured at from the Washington Marina, is about 80 decibels. An orchestra's crescendo is 90. You get rock bands are about 120, and in fact, at about 121 is considered by most experts and the FDA as causing ear damage. So rock bands will actually engineer it so that they are just loud enough where they will not cause permanent damage to your ears, but are just barely there. If you go up into the 140 range, 160 range, that's like shooting a shotgun without hearing protection right next to it. It hurts your ears. You get that ringing sensation, and you've done damage to your ears. And if you get to anything louder than that, you can actually cause irreparable damage and actually puncture your eardrum itself. Your eardrum's pressure, the pressure of that sound wave can actually damage it so far as to destroy your hearing forever. Now, sound frequencies, on the other hand, those can range from human hearing, and you'll want to write these down because these are numbers you want to know. Frequency, human hearing can be from somewhere from 20 to 20,000 hertz, and it can be heard by most people. Again, this is generalization. Older people have harder times hearing the higher frequencies, and it becomes harder to hear. And if they listen to super loud sounds or louder sounds over a long period of time, they can lose that upper frequency sound, and it's very difficult, and it can be very, very disheartening when you lose that. So when you get this noise pollution, it becomes very, very distressful for some of the older people because they can't hear anymore. In a quieter room, they're fine, but in like a restaurants or things like that, it becomes very hard to hear. If you want to, go to this website. We won't do it on the computer, but go to this website. Just type in online tone generator hearing test into a Google search, and play the hearing test. This will generate a note from 20 hertz all the way up to 20,000. And then you can actually see where your hearing cuts off at. Mine cuts off at around 16,000 hertz, so well below the 20,000 hertz limit. I blame my high school years of listening to rock music for that one. Now, frequency or pitch, note, tone, these are all words that are synonymous to each other. This is the note. So at 20 hertz, that's the lowest note you can hear. That's the low notes. That's your basses. And in your 20,000 hertz, that's above hearing. You're starting to get to the above human hearing. So as you go from low to high, your pitch increases, your frequency increases. So this is how you hear. So high frequency, high pitch, high notes, high tones, however you want to call it. Now, anything above 20,000 hertz is called ultrasound. Now, this is used in the same thing as ultrasounds used in looking at babies. That is the same thing. Anything that's used below human hearing, below 20 hertz, is called infrasound. Ultra meaning above sound, above sound. Infrasound, infra meaning below sound. So, ultrasound can, if you take a sound wave that's above human hearing, shoot it through a material, let's say the human body, and it reflects back off, this is going to create a picture, and then you can digitize it. You can do this with babies, so you can see here's the baby's head, and here's the baby's body. You can also not just do it with a pregnant woman, you can also do it with you. Here is a picture of somebody's heart. Here's your 4 chambers of the heart, and this one is a patient with a normal septum that's between, I believe this is your ventricles, and then this patient has a abnormal growth has some deposits on that septum that separates your two ventricles. That's not good. That means there's less volume inside of your ventricles. Bad things happen. So they were able to, using an ultrasound, to look inside your tissues. You may have heard of or even had yourself an ultrasound done on maybe your knees or your ankles if you've ever had any ankle or knee injuries, especially in sports, ACLs and damages. That they use that to detect if it was a tear versus a break. Now, infrasound can be used in monitoring earthquakes. This one's in, I have no idea how to pronounce that word, Greenland, and it's a microphone system that will listen for earth moving. And now it's below human hearing, but you can actually detect it, and then you can actually say that whether or not there's an earthquake or even nuclear bombs go off. Sonar is very similar. They can use both audible sound or ultrasounds or infrasounds, just depending on what they are looking at, and they can bounce off a signal using a sound. In the movies, you hear them pinging. That's literally what it is. It's a sound. It sounds like the ping, and you hear the subs can pick it up. They're like, "Oh, they're pinging us." Yep, that's exactly what they're doing. You sound a ping of a sound, ding, goes down, reflects off, and they can see images of, let's say, a downed ship. They use this to see the sea floor. Animals use this as well. Bats, dolphins, submarines send out signals of sound. It reflects off, and they're able to use the Doppler effect. So, if you have any further questions about sound and how it works, go and please ask your teacher. Thank you.